In previous lectures, we've talked about what happens when we have a multi-degree of freedom system. In a free response, we have some initial condition and no forcing, or a forced response where we have a transient case. What we want to look at now is what happens if we have a steady state excitation. So say f1 of t was some amplitude times a cosine, omega t. Or we've also seen that we can write that in a more general form as the real part of some complex amplitude, e to the I omega t. So how does a multi-degree of freedom system respond, and how is that different than and similar to a single degree of freedom system? So to do anything, we're going to need the equations of motion, so we start there. So we can derive the mass and stiffness matrices for this system. We could put in damping, but I'll just worry about that later for brevity. So these are the equations that govern the system, and on the right-hand side we'll have the force, F of t, which is a vector of forces. We don't have to, we could have a force on each of the masses simultaneously and do them in phase or out of phase. This is something that's actually done when doing ground vibration tests of airplanes. They'll actually mount the airplane on the ground and then apply forces at 2 points, and they might be in phase or they might be 180 degrees out of phase. And either of those could be written that way. The in phase case would be the two forces this way. Then we'd have, then we could have a cosine omega t. And in the out of phase case, we just have a 1 minus 1 and the same thing. So this is done to excite the different kinds of modes of the airplane and when checking computer simulations to make sure that an airplane's safe to fly. Okay, but anyway, in our present example, we have the equation of motion, we have some forcing, and what happens? If we solve the eigenvalue problem for this system, we get its 3 natural frequencies, and we get the 3 mode vectors corresponding to each of those natural frequencies. And I've written them here with some digits left off just for simplicity. So, so these are the modes of the system. By the way, it's interesting to note that we could have worked out some of these natural frequencies actually just by looking at the system. For example, if we guessed that the system might have a mode 111, what would that tell us? Well, 111 means that all of these masses are displacing the same amount. So we could actually redraw that system as one big mass. One big mass, 3 masses all joined together, and 3 springs, all K1. So in other words, that's just a 1 degree of freedom system with 3 springs in parallel, so a stiffness of 3K and a mass of 3m. And we can just look at that and we know that the natural frequency would have to be square root of 3m over 3k. And because the mass is 1/3, that ends up being third, that should be square root of 3k over 3m. So because the mass is 1/3, that gives us the natural frequency of 1.73. So we could have kind of guessed that. Similarly, actually I guess it's worth backing up and saying, I just took for granted that you would recognize that these 3 springs on the bottom, K1, these are beams, right? So a beam, when we apply a load, it can kind of deflect kind of like this. And so we're saying that can be represented as a spring with some equivalent stiffness. that spring we'd actually probably put up here like this, right? K1, and then eliminate that down there. So anyway, that's what the drawing means. And this could be a model for like a building or something. The K could be the stiffness of the walls. These masses could be the floor with some softer springs kind of allowing the floor to move in 3 pieces. So that's one thing that this system could represent. So anyway, we saw that we could estimate the first mode no problem using just some knowledge of what's happening. We could actually do the same thing with the second mode. For that mode, we'd have one mass here that's sitting still, and then what we're saying is that this mass is kind of bending in and this mass is bending back. So actually we can take either half of that system, and if we take this half, for example, we have the spring K2 and the spring K1. So we basically have that mass. We have spring K2 connecting it to ground, and spring K1, well, it's going out a different way, but it's also just eventually going to ground. So from that we could say by inspection that this has a stiffness of K1 plus K2 over M. And if you plug in the numbers, K1 and K2 are 1 and 2, so we have 3 over 1/3, and then we take the square root of that, and there's our answer. So anyway, just an interesting aside about systems. As we start to understand them, we can get some confidence that the natural frequencies that we found are actually correct and reasonable. So back to the problem we want to solve. We've got a force that's a harmonic, and remember that for a single degree of freedom system, if the forcing was harmonic, then we said in steady state, or after all of the transients have gone away, we could assume that the response was some real part of some complex amplitude e to the I omega t. And this was for a single degree of freedom system. So let's see what happens if we plug this in. And remember, with a multi-degree of freedom system, the first step. Oh, actually, before that, by the way, what could this force actually mean physically? This might mean that we've taken a machine, maybe something with a big rotor that's spinning around, and the imbalance from that rotor is going to apply a force on the floor. So this could be an air conditioner mounted on the floor of your house, or on the roof of your house, or on the roof of an office building. And we're interested in the vibrations that could be transmitted elsewhere, that could be noise, or even maybe cause failure. So anyway, this is the forcing. The first step to solving any multi-degree of freedom system problem is to make the assumption that the response in physical coordinates can be written as the mode-shaped matrix, the mass-normalized mode-shaped matrix, times the response in modal coordinates. And if we do that, we've seen several times now that we eventually end up with this set of uncoupled equations. Notice also on this right-hand side we have the mode vector transpose times our force vector. And if we plug in F, if we plug in this F, real part of F e to the I omega t, where F has just one non-zero value for the first mass. If we plug all that in, our equation eventually just becomes a scalar, real part of some scalar, times the force amplitude e to the I omega t. So this truly is a 1 degree of freedom forcing a scalar forcing, and we have a 1 degree of freedom system. So if we take analogy with what we've done before, we can then assume that eta is going to be some real part of some complex amplitude, e to the I omega t. And this is, we can rewrite this equation in general as just the jth mode of modal acceleration, the jth natural frequency. And notice though, this part here, this becomes the jth mode shape times the force vector. This is our modal force. And in this case, this would be a complex amplitude. So this tells us how much force the jth mode will feel. And in the case of mode 1, we saw that this ends up giving us a value of 1 here. For the other modes, it'll be different. Notice that's just picking off this first row. So for mode 2, we'll have a factor of 1.2, so it'll feel more force than mode 1 did. Mode 3 will feel less, and we should see that reflected later. Okay, so if we assume that each mode has a response that's some complex amplitude, and so again, we know that if the force is harmonic, the response will also be harmonic. The only thing that we're left to find is the amplitude and phase of the response. And so we plug in and we get an algebra problem then that we can solve. From the acceleration, we get this minus omega squared term. This is the natural frequency squared from the stiffness term. And so now we have an algebraic equation for the complex amplitude in. In this case, if there's no damping, this is always a real number. It's either positive or negative. And we could plot this. We know what's going to happen is that when omega approaches the natural frequency, this will go to 0, and n will go to infinity as omega approaches omega j. So if we plot the magnitude of n, we'd see something with a singularity right at the jth natural frequency. And this is the same for mode 1, mode 2, mode 3. So we would just get a bunch of these curves for mode 1, mode 2, mode 3. And so each mode just behaves like a 1 degree of freedom system. It just has a different resonance. Here I've actually plotted this from MATLAB. So these are the curves for each of the modes in the magnitude of nj as a function of amplitude. I've also, in this example, I also assigned a damping ratio of zeta equals, I think it was 0.02, and the same for the second mode, and the same for the third mode. So, so that it's not singular, it doesn't go to infinity, but it has a finite peak. What are the implications of this? If we think back to the physics of the problem, we want to mount an air conditioner on the floor here. If it was a 1 degree of freedom system, we know that we want to avoid having the rotation speed of the air conditioner equal to the natural frequency. Now, we have an even more difficult problem, because now we want the omega, which is the rotation speed of the air conditioner, to not be equal to omega 1 or omega 2 or omega 3. So we have to try to place the operation speed either in the trough between modes, or what we often try to do if we can is put it below any of the modes, or maybe way up above. But a continuous system has an infinite number of modes, so we can't really put it up there. This is typically what we have to do for a variety of systems, is engineer them so that we can choose that resonance frequency to be away from any natural frequency of the structure. All right, so a lot of structures are actually designed this way. One example is a helicopter. Helicopter is a airframe with lots of resonances, lots of flexible components. So if we were to plot this kind of thing for a helicopter, we would see lots and lots of different peaks and lots of different points where this could go into resonance. And we'd have to design the operation speed of the helicopter. Helicopters actually have a rotor that spins at a constant speed. So that rotor on the top of your helicopter, here's a little Harold the helicopter, right? That rotor actually spins at a constant speed, and you vary the pitch of the blades to vary the amount of thrust. And the reason for that is you choose the operation speed to be at one of these magical frequencies away from any resonances of the helicopter. If you don't do that, you could hit a resonance and destroy the helicopter. Let's actually look at an example of that. So here's an interesting example of a helicopter resonance. So I believe this is a Chinook helicopter, and notice they've strapped it down for a test. And the act of strapping it down kind of rigidly to the deck here actually will change the resonances, change the natural frequencies of the helicopter. And so it's moved the resonance of the structure, of this helicopter structure, to be closer to the operation speed of the helicopter. So, sorry, didn't mean to do there. Sorry, let me just go back real quick. In any event, what we will see here, if we can get this working. All right, so in this case, we see the helicopter, as the rotor spins, it will hit a resonance of the whole structure. And it's really causing the whole helicopter to shake. The amplitude of vibration grows a lot as the forcing is coming close to the natural frequency. And you see you're starting to tear off pieces of the helicopter and rip things apart. And eventually the whole helicopter destroys itself. So all of that is due to this simple phenomenon. Here's a side view just so you can see a little better what's happening there. So again, we hit a resonance which causes the amplitude of vibration to go way up. And as the amplitude of vibration goes up, the stresses on everything go up. The smoke must mean we break some kind of oil line or something to do with the engine. And the whole helicopter is destroyed. So we don't want that to happen when we're flying, right? So anyway, that's why so much effort goes into designing things like helicopters and airplanes to try to avoid these types of resonances. And so what you saw there is that the speed of the engines came in line, say, with one of the modes, and so you get a large increase in the vibration amplitude and failure of the helicopter. Hopefully that makes sense now. The last thing we haven't talked about is there's one more important step, and that is that what we found so far were just the modal coordinates. And what we really want to know is how that maps back to the response of these three masses here. So we can actually work that out if we assume that x is the real part of some complex amplitude e to the I omega t. Actually, I guess this actually falls out of what we've just done. We made the assumption that each of these etas was the real part of some scalar complex amplitude e to the I omega t. So because of that, if we plug that all in, this whole thing is just a matrix times a bunch of constants. So we could actually show that the response x has to have this form, where this matrix x is given by this expression over here. It's just the mode-shaped matrix times the complex amplitudes n1, n2, and n3, or the complex amplitudes of the three modes. So, and we could get the complex amplitude as a function of frequency. It will just be each of the mode vectors times its modal complex amplitude, which is also a function of frequency. That's these three curves up here. And then we add those up for all the modes. And things become nice and clear and simple because you notice that each mode only peaks at a single frequency. So when we come to the first natural frequency, we'll see every mass moving in proportion to the first mode shape at that frequency. So the resonances that occur separately for each mode can occur in every one of the masses. And that's exactly what we see here. When we get to the first natural frequency, we have equal amplitudes. And that comes about because the first mode shape was 1, 1, 1. So we get equal amplitude of the three masses, and all of the whole structure will move as a rigid body side to side. When we get to the second mode, though, it looks peculiar. Hopefully that's not too much of a surprise if you remember that mode we had a 1.2, a 0, and a negative 1.2 for the mode shape. So basically that mode has a 0 amplitude. I guess it's not eta 2, it's the phi 2 is equal to 0 right there. So that mode doesn't show up. This red curve, as far as mass 2 is concerned, this red curve gets multiplied by 0. And so here we see just these two peaks. We get one with a plus 1.2 amplitude and one with a minus 1.2 amplitude, but since we're taking the absolute value, they look like they're the same. And the same things happens at the third natural frequency. So using this, we can understand all kinds of things about multi-degree of freedom response and how and predict how a structure will respond. And we can understand that all in terms of these simple modal responses and a few concepts. The important concept is the force. And notice the force comes about by the mode shape transpose times whatever our forcing vector is. And then the response comes by grabbing a row here where we have to look at the mode shape at the same element in each mode shape. So for example, for this, for x1, we would look at these values. And those tell us how strongly the mode will respond. Let's say one other interesting thing about the forcing. For mode 2, we have this interesting interesting mode vector where we have a 0. And that's not a strange occurrence. Real structures will have all kinds of zeros, especially if you think about the modes in different directions. And anyway, this is a common occurrence. Well, let me just give you one example. Imagine we're talking about an airplane, and we're looking at the wing, and say this is a top view, and we could also draw a side view of the airplane. So this airplane wing will have some modes that move up and down in this direction, and it will have some modes that move in this direction or into the page in this view. So all of these modes in the different directions will have a 0 in the opposite direction. So anyway, a 0 in a mode shape is not an uncommon thing. And what that means, though, is that when we go to compute the force, we'll have phi, the mode shape transpose times a force vector, and in this case we had F1, 0, 0. So if instead we applied the force at the second mass, so let's suppose we put a force here, F2 of t. If we do that, notice that phi2 transpose times 0, F2, 0, that's just going to give us 1.2, 0, negative 1.2, and the force is actually 0. So if we applied the force like that, these curves would look totally different. We would see nothing at all right here. This curve would just continue. And similarly, there'd be no response in this point either. The mode would be completely absent because its force is 0. And so no matter, basically that makes this value of n2 go to 0 so that the second mode doesn't show up at all. So that's an important fact that we use when we design tests, and something that we talk about quite a bit in EMA540, if you're able to take that at some point. All right, so that concludes our discussion of forced response, modal forced response. We'll learn a different way to solve for the modal forced response in the next lecture, and we'll see some additional examples.